So, hi everyone. We will start at our usual time, that is 3 or 5 p.m. Waiting for some students to join in. Then we can start. Good afternoon, everyone. Today we'll discuss weak streaks related problems. I think we'll start after 1 minute. I think we can start. So before we start, let me just lay out some guidelines. Guidelines are same as always. I'll just solve a problem and give you some time in case of any doubts. You can ask in your doubts as the attendance is quite low today. So I think you can use your microphone to ask in your doubts. If you're comfortable, also you can use your the chat box also. So then let me just share my screen first and then we can start. Just a second. So let's start. So again, I welcome you all to this live session 6 of the course Digital Circuits. The course is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur and I'm your course TA. My name is Musaf Rafiq. I am a PhD student at the Department of Electrical Engineering at IIT Kanpur. Today we are going to discuss the problems related to week 6 material of this course. The problems will consist related to sequential circuits and some of the problems from the past week's material like Mux, Tmux and all. Mostly we'll be focusing on sequential circuits. Just a second, I'll admit a participant, then we can start with the problem number 1. So let's start. And also during the course, you can keep your videos and mics set. So here we have a question. It states that which of the following circuit can be used as a series to parallel converter. So we are given the four options and we are asked to figure out which of the circuit can be used as a serial to parallel converter. So before we proceed to our answer, let me just say what we really want. Suppose we have a black box. We need to figure out what this black box should be. We have this black box and we have a serial input. And this black box, what it does, it routes this input to one of the outputs. So here we have a serial input like this, and here we will have a parallel output. So among the following, you people might be aware, a demux does this thing. So what a demux essentially, so what do we really want is something like this. We have a function f, just a second. We have a function f which is connected to a common source line. We have a common source line here, or you can call it a common input line. And what it essentially does, we have something like this. These are switches connected to different outputs, parallel outputs. Let's just say A, B, C, D. And here we have two, what we can call as control lines. We have control lines. And in what among the options, our demux does this kind of a thing. Here we have a serial input and based on the combination of control lines. So in demux, what is a control line? Simply your select lines. Based on the combination of select lines, this input gets routed to one of the parallel output. So among the following option, a demultiplexer does this thing. It converts a serial, it's used as a serial to parallel converter. So any doubts in this question? Yeah, someone has written answer. Well done. So demux simply is your serial to parallel converter. Now let me just move forward to question number 2. It states that a PLA, a programmable logical array. Just a second, sorry about that. Someone wants to join the meeting. Sorry about that. So a PLA, which is a programmable logical array, consists of, it's a simple theoretical question. You people are aware of this. A programmable logical array consists of a programmable AND gates and a programmable OR gates. We have a programmable fixed and we have a programmable AND gates, and then we have a programmable OR gates. It's a simple theoretical question. You can refer to your lectures for more details on this. So a PLA simply consists of a programmable AND gate and a programmable OR gate arrays. So option B is the right answer to this question. Now question number 3, I would like you guys to answer this first, then I will just discuss it. This SR latch is an example of ABCD, a combinational circuit, a synchronous sequential circuit, a 1-bit memory element, a 1 clock delay element. So as SR latch is an example of what? So you can type in your answers and then we can discuss it. So I'll just repeat the question. The SR latch is an example of, and we are given these 4 options. Option A, option B, synchronous sequential circuit, option C, 1-bit memory element, and option D, 1 clock delay element. So one of the students have written the answer, 2 of the students, but only one of them is correct. So this SR latch is simply a 1-bit memory element. When we talk of these SR latch flip-flops, these are this basic memory element. They are 1-bit memory element. When you talk of this SR latch, so this is a basic memory element that you can think of. So whenever you think of this SR latches, think of it as a 1-bit memory element, always, nothing else. It's a 1-bit memory element. Now we have a question number 4. It says that a JK flip-flop with the condition J equal to 1 and a K equal to 1, that are the 2 inputs to the JK flip-flop, has a 20 kilohertz clock input, right? So what we are given is a JK, we are given this J and we are given this K, and what we are given this, we are given this J and K, and finally we have this here Q and Q and Q bar. So we need to figure out the output frequency when the input J and K are equal to 1. So before we proceed, let's just draw the characteristic table of this JK flip-flop. So I would like you guys to help me out with this. So we have this clock, and then we have the 2 inputs J and K. Here we have this output Q n plus 1. Just a second. Actually, my mouse is not working. Let me just try with this. Yeah. So when clock is 0, we have a don't care on J and K. What will be this output Qn plus 1? Can someone tell me? Any of you? So when clock is equal to 0, J and K are don't here. So what will be my output? Qn plus 1. So no change. Yeah, no change. How do we represent this no change? Yeah, some of you have written the answer. That's nice, but let's just go step by step to the answer. No change. You represent Qn plus 1. No change means. Yeah, you can use your microphone. Any of you. Yeah, Qn exactly. So this Qn will be equal to Qn. We call it as a memory condition, right? Now when clock is 1, J is equal to 0, K is equal to 0. What is Qn plus 1 be? Again, I'm asking you what this Qn plus 1 be for 0, 0. Yeah, Qn. Nice. So this will be Qn again, and we term these two conditions as memory, right? Now when clock is high, let's just write clock high for all other cases. So we have 0 and we have 1. What will Qn be? It will be 0. And when it is 1 and it is 0, we have 1. And finally for 1 1, what will be the condition? When j is equal to 1, k is equal to 1, what will be Qn plus 1? When j is equal to 1, Qn plus 1? Qn bar. Yeah, nice. So this will be Qn plus Qn bar. This will be Qn bar, right? So far we are all on the same page. Now what we have a clock of 20 kilohertz. Let's just assume this is a positive edge triggered flip flop. We have a clock of 20 kilohertz. Sorry about that. It should be similar symmetric, but forgive my drawing. Actually, I'm drawing with a mouse. And the frequency of this is 20 kilohertz. And our input is always 1 1. J is equal to 1, K is equal to 1. So Qn plus 1 will be, this is your output Qn plus 1. Let's say it was 0 here. So at this triggering, it will be Qn bar. Then again at the positive edge trigger, it will be Qn bar. Similarly, all of this. So if f was equal to 20 kilohertz, f dash, that is the output clock frequency, will be equal to f by 2. This you can see here. So what is the time period of this? Let's just say t, and for this is 2t, which translates the frequency of f by 2. So if f was 20, f dash, that is your output clock frequency, will be 10 kilohertz simply. So option D is your correct answer. Some of you had already written. These things are quite simple, but I just wanted to go from step by step. Why are we doing this? How we end up at this situation? And if your basics are clear, you can have just directly given the answer 10 kilohertz. That's not an issue. Now, this was the question number 4 of today's live session. Now we'll move forward to question number 5. So this question number 5, I would like you guys to do first. It will take 4 to 5 minutes. So that I will just assume I'll give you 5 to 6 minutes, and you'll give me the answers at the end of the 5 6 minutes, and then I'll show the solution. First, let me spell out this question for you. For the clocked flip-flop circuit, for the clocked flip-flop circuit shown below, what is the correct characteristic equation? So you are given this clock flip-flop circuit, and you need to figure out what is the correct characteristics equation. So you are given, I will give you 5 minutes, and you can solve it, and then I'll show the solution. So has anyone done it? Are you guys doing or so only one of the student has given the answer. So now let me just show the solution. So we are given this clock circuit and we have clock pulse. Let's for sanity assume this clock is equal to 1, and also let's just term these inputs as A star and B star here. So when A is equal to 1 and clock is equal to 1, this A star will be equal to 1, and when A is equal to 0, this A star will be equal to 0. So simply these input get passed to this. So there is no change to input. This is only the clock that will dictate the input. So for our consideration, we have taken clock equal to 1. So A star, B star are simply A and B because we have taken clock equal to 1. Now let's just take a look at this table. This thing, what is this? This is simply an SR latch. Let's construct this. This is your A and B, simply A star, B star. And when we'll just draw the characteristic table for this. A, B, and Qn plus 1. So when A is equal to 0, B is equal to 0, this thing will be equal to Qn. That is the memory condition. And when A is equal to 0, B is equal to 1, this will be 1. If it was a NAND gate, it would have been 0. Since it's an OR gate, that's why it's 1. And when A is equal to 1 and B is equal to 0, Qn plus 1. So let me just write this is Qn and this is Qn bar. So this will be 0, and finally we have 1 1, which is the invalid condition, right? Now let's just draw the truth table for it. A, B, and Qn. Sorry about this mess up. Actually, my mouse is not working quite well today. So this is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and finally we have 1 1 1. Here we have qn plus 1, right? So when a equal to 0, b equal to 0, we have condition qn plus 1 will be equal to qn. That is a memory condition. So this is simply 0 1. When a is equal to 1 0, b is equal to 1, we have the condition qn plus 1 will be 1 1. So we have this 0 1 1. Then when a equal to 1 and b equal to 0, we have this 0 0. And when a equal to 1 b equal to 1, we have the condition that is invalid. Now using this truth table, we need to construct the characteristic equation out of it. So what we'll do, we'll take help of this K-map. Here we'll write A, here we'll write B, and here we'll write Q. Q is simply your QM. So this is like this. Kindly check these things. If I'm wrong, please correct me. And these are your don't care conditions, right? So you have 3 ones and 2 don't cares. This is your A bar and this is A. So let me just write this is 0 0 0 1 1 0 1 1. Sorry, 1 1 1 0. So that's why I was saying that kindly look at this, and this is A bar and A. So what you can do, you can construct this pair, and using these don't cares, you can construct a chord. So your qn plus 1, that is simply among the options q of t plus 1. So your qn plus 1 will be equal to the term coming out from this chord, that is b, and the term that coming out from this pair, that is a bar q. So your characteristic equation is q of n plus 1 b plus a bar q. Now there is also a second condition you need to figure out, that is ab. So if you carefully look at these tables, for condition a equal to 1 b equal to 1, you have an invalid condition at the output. So that means a b, that is the AND operation between a and b, should always be equal to 0, because if a b is equal to 1, you will get an invalid condition. So your a b, this is valid for only a b equal to 0, right? Otherwise we will have invalid condition. So what we'll have, we have qn plus 1 is equal to b plus a bar q, and a dot b is equal to 0. That is option A is your correct answer. So one of the students had solved it correctly, others also tried. That's nice. So now let's just do question number 6. By the way, any doubts in here? If not, let's just move forward to question number, what was this, 5 6 of today's live session. So we have this circuit. So the above synchronous sequential circuit, which is built using JK flip-flops, is initialized with Q2, Q1, Q1, Q0 equal to 0, 0, 0. The state sequence for the next 3 clock cycles will be, so we need to figure out the state sequence for the next 3 clock cycles. So we are given these 3 clock synchronous circuits built by. So I would request all of the students to kindly turn off their videos. Yeah. So this is built using JK flip-flops, and you need to figure out what will be the state sequence for the next 3 clock cycles. So before we proceed to finding out the state sequences, let's just draw the characteristic table for JK flip-flop. We had already done it, but we'll do it again, because these things we need to do again and again. So this will help us. So you have here Qn plus 1. So you have J we have K. So for 0, 0, as I already discussed with you, we have a condition of memory, that is Qn. For 0, 1, it is 0. For 1, 0, it is 1. And for 1, 1, it is a toggle condition, that is Qn plus 1 will be equal to Qn bar. Now we need to do, we will draw a table. So let me just draw the table. Insert a table 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have a table. So this is your initial states Q2, Q1, and Q0. This right here will be your, this right here will be J1. Then it's let me just write this at J2 because this first flip flop is J2. Then we have K2, then we have J1, then we have K1, then we have J0, then we have K0, then we have finally Q2, Q1, Q0, right? So this J2, this J, input J, is connected to where? Is connected to Q0, right? No. This J2, this thing, is connected to Q1 bar. See from here, Q1 bar. So here I will write J1 is equal to Q1 bar. Now this K2 is connected to Q0. Then J1, see the J1 is simply connected to Q2. This is connected to Q2. Then K1 is connected to Q2 bar. Then J0 is connected to Q1 and K0 is connected to Q0 bar, right? You can take a look at this again. If there are some mistakes, do correct me. Now what we are given is this initial condition. We start from 0, 0, 0. So that means we have Q2 equal to 0, Q1 equal to 0, and Q0 equal to 0, right? So that implies our J2, which is equal to Q1 bar, will be equal to 1. Our Q2 is equal to Q0, that will be equal to 0. Our J1 that is equal to Q2 will be equal to 0. Our K1 equal to Q2 bar will be equal to 1. Our J0 equal to Q1 will be equal to 0, and it is Q0 bar that is equal to 1, right? Now Q2 will be depending on J2 and K2. So J is equal to 1 and K equal to 0, so it is 1. Then we have J1 K1, so that is 0 1, so that is 0. And then Q0 will be equal to J0 dependent on J0 K0, that is again 0. Now our condition for this cycle is 1 0 0, right? Now that implies Q1 is again equal to 0, Q1 bar will be equal to 1, Q0 is 0, and Q2 which is 1, so it will be 1, Q2 bar will be equal to 0, then Q1 is 0 and Q0 bar is 1. So again we have J2 equal to 1 and Q2 equal to 1, that is 1 0 K, so I'll have 1 here. Then J1 1, K1 1, I'll have 1 here. And finally J0 equal to 0, K0 equal to 0, I'll have 0 here. Now what will be my condition for the next clock cycle? That is 1 1 0, right? So Q1 will be equal to 1, so Q1 bar will be equal to 0, and Q0 is 0. Then Q2 will be equal to 1, Q2 bar will be equal to 0, Q1 is equal to 0, Q1 is equal to 1, and Q0 bar will be equal to 1. Let me just check it again. J0 is equal to Q1, so that is equal to 1, Q0 bar is 0, and so it will be 1, right? Yeah. Now 0 0 means memory, so it will be 1 only. 1 0 will be 1, 1 1 will be toggling, it was 0, so it will be 1, right? 0 bar. So These are the conditions for us. So for the three clock cycles, after three clock cycles, what are my states? My states are 100, 110, and 111. So that is option C. Option C is my right answer. So option C was correct answer to this question. Any doubts? If not, let's move forward to question number 7. So this right here is an important part of this today's live session. This question number 7. So we have a conversion problem at hand. So using one flip-flop, we need to construct another flip-flop. So we have a T flip-flop and we need to figure out how we can use this T flip-flop so that we can use it as a D flip-flop. Sorry, just a second. Some student wants to join in. So let me just read this question again. We have a conversion problem at hand. So this conversion asks us convert a T flip-flop into a D flip-flop. So we are given a T flip-flop and somehow we need to do some analysis and we need to show that how we can use this T flip-flop as a D flip-flop. So whenever we have these conversion problem at hand, we should take note of 5 steps. We should always keep note of these 5 steps and we should sequentially follow them and ultimately we'll get our desired answer. So these 5 points to remember while doing a conversion problem are: number one, identify available and required flip-flop. So you need to identify which are the available flip-flop, which is the required flip-flop. Then we have to make characteristic table of required flip-flop. So keep in mind, so first of all, we need to be clear which is the required and which is available. After that, we need to make a characteristic table of the required flip-flop, right? And then we have to write the excitation, make or write, you can say, excitation table of the available flip-flop. And then we have to write the Boolean expression of the available flip-flop. Once we have the Boolean expression of the available flip-flop, then we can use that Boolean expression and we can draw the circuit which will give us the final answer. So before we proceed, I'll again read these 5 points. And these are quite important. And whenever you are doing these sequential circuits problem, you'll definitely, in terms of the theoretical exams, you'll definitely get one type of problem based on conversions. At least from my own experience, you will get one problem based on the conversions while appearing for your exams, your semester exams. So 5 points you have to remember. First of all, you need to identify the required and the available flip-flop. Number two, you need to make the characteristics table of the required flip-flop. Number three, you need to make an excitation table of available flip-flop. Number four, write the Boolean expression of available flip-flop. Number five, you have to using that Boolean expression, you can draw the circuit. So what is the problem at hand? You have to convert this T flip-flop to a D flip-flop. So if I ask you this T flip-flop, so two things you need to write. First is available. So in short, I will write this AV, which is the available flip-flop here. It's simply T flip-flop because we have to convert this T to D. So T is your available. So in short, I can write it as TFF. And which is your required. So T is your available and you need to convert this T to D. So the required is D, right? So far we are clear with this thing. And as such, option, that is point number one, we are done with. Now we have to make the characteristic table of the required flip-flop. So what we have to do, just a second, something happened to this. I'm not able to get rid of this pointer somehow. Yeah, finally. So what we need to do, we have to write down the characteristic table of the required flip-flop. That is point number 2. So let's just write the characteristic table of the required flip-flop, which is a D flip-flop. So 0 0 0 1 1 0 1 1. So Qn plus 1 for a D flip-flop is equal to D. Whatever is the input, you will have the output. So point number 2, that is making the characteristic table of the required flip-flop, is done. Now we have to make the excitation table of the available flip-flop. So which is the available flip-flop? That is T. So we write T here, right? So excitation table of T flip-flop. Take a look at this Qn and Qn plus 1. So it is 0, 1, 1, 0. How I come up at this? So you have this thing Qn. So Qn plus 1. So you know that for T flip-flop, we have these conditions. Now the excitation table of L flip-flop is done. Now what you need to do, you need to write the Boolean expression of the available flip-flop. So that is T equal to something, you need to write it. So you can draw a box K map. So if you simply look at this, even if without looking at the without taking help of K map, this is simply an XOR operation between Qn and Qd. So T is equal to Qn XOR with D. So your T, that is the input to the available flip-flop, is equal to Qn XOR D. So your final circuit will look something like this. So this is your T flip-flop, this is your input, this is your output Qn, this will go here, this will go here, here, and there is another input, that is D. Here you will have an XOR gate. So this is XOR gate, so this is D XOR Qn, and finally this whole circuit will behave like a D flip-flop. So someone has written already T is equal to D XOR Q. That's right. So keeping this methodology in mind, you can always have any of the conversion problem and you can solve that problem accordingly. So you need to keep note of the 5 points. That is, you have to figure out the available and required flip-flop, write the characteristic table for the required flip-flop, write the excitation table for the available flip-flop, write the Boolean expression, and then draw the circuit. Now based on this, we have another question, which is which of the following circuit converts a JK flip-flop to a T flip-flop? So again we have a conversion problem. So here we have a JK flip-flop and we need to convert it to a T flip-flop. So before doing anything, let's just write point number 1, that is available flip-flop, which is JK, and required is your T flip-flop, right? Now the second step is to write down the characteristic table of the available required flip-flop. So what we have to write is the characteristic table for the required flip-flop. So here you will have QT, here you will have QN, and this is your QN plus 1, right? So this is 0, 0, 0, 1, right? And this is simply toggling of this is 0, 1, 1, 0, right? Now this was the characteristic table of the required flip-flop. Now we need to write down the excitation table of the available flip-flop. So just a second. Now we have J and we have K here. So before writing the excitation table of, let me just draw. So excitation of table of JK flip-flop. When Q is equal to 0 and Qn plus 1 equal to 0, we have 0, X. I assume you know these things from your lectures. And when Qn is equal to 1 and Qn 1 plus 1 is equal to 1, so this is 1x. So this is 0x. So this is 0x. And when Qn is equal to 1 and Qn plus 1 is equal to 1, this is x0. When Qn is equal to 1, 0 and Qn plus 1 is equal to 1, so this is 1x. And then we have finally x1. So these x are basically don't cares here. So this is your point number 3. Now point number 4, which is your that you have to write the Boolean expression. So we'll take help of K-map. First we'll write, we have to write Boolean expression of available flip-flop. So this is J. So here it is T, and then it is Qn. Which we are writing this for J. So like this, we can construct a pair. So that implies J is equal to T. And now for K, we have this T, Q, and then like this. How I'm writing this? I'm writing from this. So again, we have K equal to T. So that means J equal to K equal to T is your answer. And if you have to draw the circuit, so these are your J and K. These two will be equal and they are connected to T. So this thing will convert the JK flip-flop to a T flip-flop. And this is your option number, I guess, A. Option A is your right answer. J equal to K equal to T will convert a JK flip-flop to a T flip-flop. So any doubts in here? So usually what happens here, actually the doubts usually, I mean to say the mistakes I used to make when writing the excitation table. So you need to write the excitation table based on these two conditions here. Sometimes because we have solved so many problems, we know the excitation table of JK flip-flop is something like this: 1, 0, this thing, x1 and x0, and we directly write these things. But we have to look at these conditions. This is for 0, 0, 0, 1, 1, 0, 1, 1. Here it was 0, 0, 1, 1, 0, 1, 1, 0. these are some of the points you need to keep in mind to avoid any mistakes. Then we have question number 9 of today's live session. I would like you guys to do this first. So it says that how many flip-flop circuits are needed to divide by 16? So how many flip-flop will be needed so that we can get a divide by 16 at the output? So you guys can give your answer, then I will show the solution. So some of the students have done it. It's a simple question. You might have already done these types of question. So this mod 60, this divided by 16, we call it as modulus. So this modulus, so we have this condition, the modulus should be less or equal to 2 raised to power n, where n is your number of flip-flops. So this 2 that implies 2 raised to power n, that is the minimum number of flip-flops required to achieve this modulus. This mod is simply a divide factor that we get at the output. 2 raised to power n should be greater or equal to 16. So that implies n should be greater or equal to log 2 of 16. That implies n should be greater than 4. So the minimum number of flip-flop circuits needed to achieve the divide by 16 is 4, as some of you have rightly pointed out. Now towards the question number 10 of today's live session, it states that a programmable logical array, that is logic array, shown in the figure, we have to write the Boolean function f implemented by this PLA. So before proceeding, let's just mark some of the points. So it's P, so this will be P, this will be P bar, this is Q, this is Q bar, this is R, this is R bar simply, and then we have points these that are marked. Here they are already written, but I wrote it again. So let me just write as 1, 2, and 3. So 1 will be equal to, so let me just write f1 is equal to, so f1 will be equal to p bar. So take a look at this line that is going here. f1 is equal to p bar q bar and then r, right, and operation between these C signals. Then f2 will be equal to f2 p bar q and then r. Then f3 will be equal to, take a look at this line, p q bar r, right? So we'll check it again. F1 is equal to p bar q bar r, f2 is equal to p bar q R. F3 is equal to PQ bar R. So my final expression for F will be equal to, that is the Boolean function F that is implemented by this PLA, is F1 plus F2 plus F3, and that is equal to P bar Q bar R plus P bar Q R plus P Q bar R. So the F that is implemented by the following PLA is this. Just a second. Implemented by the following circuit is this. So the function F implemented by the following circuit is this: P bar Q bar R plus P bar Q R plus P Q bar R. Now we have question number 11 at hand, which states that a 1 megahertz clock is applied to JK flip flop where J equal to 1, K equal to 1, and what is the frequency of the flip flop at the output? So a JK flip flop with 1 megahertz clock having the condition as J and K equal to 1, you need to figure out what will be the output frequency. We are done already this type of question. I expect you guys to do it quickly. And so R B bar plus 2. Someone, is there any doubt regarding previous question? Is there any doubt? If not, you guys can write. Can we simply, after writing expression for can we? Okay, simplify. Yeah, you can simplify. But in PLE, we usually write this. Yeah, yeah, yeah. I got your point. Yeah, you can simplify. But this was a theoretical question, so you can simplify. When you have this, what should I say, MCQs, based on the options, you have to take a look at the options and solve it. Yeah, you can further solve it. Yeah, there is no issue. You can solve it. For your own practice, you can solve it. But I think for PLE, you keep all the you keep it in min terms, maybe. Yeah. So now towards this question number 11. But if you have to keep it in canonical form, you don't need to simplify. Otherwise, you can simplify. I don't think there will be any issue. Question number 11. 1 megahertz clock is applied to JK flip flop with J equal to 1, K equal to 1. What is the frequency of the flip flop at output? So one of the students has already given the answer. Basically, 1 JK flip flop, it will divide it by 2. It's a simple question. So that is, if it's a 1 megahertz, it will be 1 megahertz divided by 2, that is 0.5 megahertz, that is 500 kilohertz. So to the students that joined late, we can take a look at this question where we had this condition J equal to 1 and K equal to 1, and our output input clock was 20 kilohertz, and finally our output was 10 kilohertz. So here I showed this, what should I say, this characteristic table, and I showed this for 1 1 we have toggling at the rising edges of the clock, and based and accordingly the output frequency gets divided by 2. So here also the output frequency f dash, I don't know what has happened to my mouse today, f dash will be equal to f in by 2, that is 1 by 2 megahertz, that is 500 kilohertz, right? Option B. I don't think anyone will have doubt in this question. It's a pretty straightforward question. Now we have this question number 12, and we need to figure out What does the following flip-flop configuration does? So I don't know whether this question is grammatically correct or not, but we need to figure out what this following circuit do. So we are given this D flip-flop where the output is connected, input is connected to Q bar, and we need to figure out what it essentially does. So before we proceed, I'll just draw a table first. So before we proceed, let's just assume our initial condition is D equal to 0. D equal to 0 is our initial condition. Here we have this clock cycle, then we have D which is equal to Q bar, and then we have Qn plus 1, and this is Qn plus 1 bar. So for a first clock cycle, that is initial clock cycle, I'll call it as I. D is equal to 0. D is equal to 0, that implies Qn plus 1 is equal to 0. Qn plus 1 bar will be equal to 1. So now the first, second, third, fourth clock cycle, here I will write. So D is equal to Q bar will be 1. So that implies Q1 will be 1, and this will be 0. This will be 0, this will be 1, this will be 0. This will be, this will be, I think, 0, 0, and this will be 0. Okay, 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 okay. This is 1. Okay, yeah. This is 0, this is 1, this is 1, this is 1, this is 0, and this is 0, this is 0, this is 1. So if you carefully look at this, after every clock cycle, after every two clock cycles, that is, take a look at from this 1, 2, after every two clock cycles, the input repeats. So it is a simply 2-bit counter. So how after every two clock pulses the value repeats, and how many values it counts? 2, that is 2 raised to power 1. So it is a 1-bit counter. So the following circuit acts as a 1-bit counter. So option C is the right answer. So I'll repeat it again. We have assumed D equal to 0 initial condition. Even if you assume D equal to 1, the same thing will happen. Then it will go from 1, it will go from 1 0 1 0 1 0. That's the only thing that will change. The rest of the things will be same. So initially I have assumed D equal to 0. That implies Qn plus 1 equal to 0, and Qn plus 1 will be 1. Then after first clock cycle, D equal to Q bar, that is 1. Qn plus 1 be equal to D, that is 1, and Qn plus 1 bar will be equal to 0. Then 0 0 1, then 1 1 0, and 0 0 1. So after every second two clock pulses, the value keeps on repeating, and that means it counts two values. So it is a 1-bit counter. 0 1. It counts two values. It is a 1-bit counter. So one of the students have given the correct answer. That's nice. Now, and this was question number 12. Now we have question number 13 to discuss. It states that, so I would like you guys to do first, and then I'll show the solution. It states that the output of the circuit in the circuit, the output of the circuit shown below will be. So basically, you need to figure out what will be the frequency of the output of the circuit shown below. So write the frequency of the circuit output. Write the frequency of the output shown of the circuit shown below. So your input clock is given as 1 kilohertz. So you need to write down the output clock frequency. Yeah, some of you have done it and done it correctly. So we have in these types of question, the output clock frequency, that is F out, will be equal to F in divided by 2 raised to power n, where n is your number of flip-flops in the cascaded configuration. So how many flip-flops are there? 8. So it's 3 Fn divided by 2 raised to power 3, that is Fn by 8. Fn is your 1 kilohertz, so 1 by 8 is 0.125 kilohertz. Never forget units. And 0.125 kilohertz simply means 125 hertz. So option A, as some of you have already written, is the correct answer. Now, question number 14, it states that a mod 2 and a mod 5 up counter, when cascaded together, results in a mod dash counter. So when two mod up counters are cascaded, we have so mod m, where m is the modulus of the cascaded configuration, is equal to mod m1 times mod m2. So here mod m1 is 2, mod m1 is 5, so it's 2 multiplied by 5, that is 10. That is option D. Yeah, some of the students have done it. So let's just take a couple of minutes break, then we can resume. So we can resume. So question number 15, it states that the output of a JK flip-flop with asynchronous preset and clear inputs is 1. The output can be changed to 0 with one of the following conditions. By applying J equal to 0, K equal to 0 and K using a clock. So let's just examine individual outputs. So if you apply J equal to 0, K equal to 0, it will remain at the same position, so it will not change. By applying, let's see option C, by applying J equal to 1 and K equal to 0 and using the same, it will again be equal to 1. By applying this synchronous preset input, it will not change. So the only condition which will change the output is by using option B, which is J equal to 1 and K equal to 1, which is the toggling condition. It will change the output. So option B is the correct answer to this question. Any doubts? So someone has asked, sir, this formula is only for T and JK flip-flop or any other also. So I assume this was for, let me just check. This was for question 13. Yeah. So this is for toggling conditions. You see, you have this T equal to 1. Why this T is equal to 1? This means toggling is happening. So when J equal to 1, K equal to 1, T, we are saying toggling. So yes, it's for the toggling we are saying. Yeah, this condition. Now we have discussed question number 13 and 14 also and 15. Now we need to discuss question number 16. So what we have here is two D flip-flops are connected as a synchronous counter that goes through following sequence 00110110. The combination of inputs DA and DBR. So we are given this present state, the next state, and we need to figure out what are the combinations of input. So what we'll do here is we'll draw the table. Here I'll write present. This is the present state. So I'll write Q B Q A. This is next state. So I'll write this as QB plus 1. So this is QA plus 1. Then I will have inputs. So these are DA. These are DA. Now what is given is QB QA. QB is equal to 0 0. Then I'll go from 1 1. Then it is 1 1. I'll go from 0 1. Then from 0 1 I'll go to 1 0. Then from 1 0 I'll go to 0 0 again to the start. So now let's just write the inputs db. So db, so qb plus 1 is equal to 1. So that means db is, because for a d flip flop q is equal to d, qn plus 1 is equal to d. So db qb plus 1 is equal to 1. So that means db is equal to 1 and da plus 1 is also 1, right? Then we have 0 and 1. Then we have 1 and 0, and then is 0 and 0. Now let's draw the k map for this. So this is for DA. DA is simply, so DB, sorry, DB is simply QB bar. So if you look at this DB and QB, DB is equal to QB bar. Now I have DA. For that I'll take help of this KMap. So here I'll write QB and here I'll write QA. So this is 1 0 1 0 1 0 0 0 0 1. Then I will write 0 1 1 1 1 and 0 0 1 1 1 1. Yes. So these two terms. So dA will be equal to QA bar QB bar plus QA QB. That is the XOR operation, simply XNOR operation. So my dA is equal to QA bar QB bar plus QA QB, and dB is equal to QB bar. That is option D. So option D is the right answer. So what we did, we first wrote the present state input and the next state present state outputs and next state outputs. Then we wrote the inputs based on the outputs, and then we wrote the this combination of inputs of dA and dB. So what we got is dB equal to QB bar, dA is equal to QB QB QA QB plus QB bar QA bar. That is option D. Now I would like you guys to do this question. So it says that a feature that distinguishes the JK flip-flop from the SR flip-flop is the A, B, C, D. You have three options and you need to write the correct option. So a feature that distinguishes JK flip-flop from the SR flip-flop is, so as most of you have written it, so the feature that distinguishes JK flip from the SR flip-flop is toggling condition. The toggling condition is not present in JK flip-flop. It's sorry, SR flip-flop. It's only present in JK flip-flop. Now towards question number 18. A forward counter is used to count from 0, 1, 2, 3 up to n. What is the value of n? So can someone tell me what will be the value of n? So let me just show the solution. A 4-bit counter. So n is equal to n dash. Let's just write n dash for sanity. N dash is equal to 4. So a 4-bit counter is will be a mod 16. That is, it will count 16 states. That is from 0 to 2 raised power n minus 1. So the maximum number it will count is 2 raised to power n dash. I should write n dash. 2 raised to power 4 minus 1, that is 16 minus 1. So the maximum number it will count is 15. So the number of, so it will count from 0 to so on up to 15. So the maximum number it will count is 15. So the value of n here will be 15. Now question number 19. It states that three T flip-flop are connected to form a counter. The maximum states possible for the counter is. So what will be the maximum number of states possible for the counter? Yes, it will be 8. So how? 2 raised to power n, that is 2 raised to power 3, that is 8. Option D. Now I have this question. The state transition of T flip-flop from 0 to 1 requires. So the state transition from T flip-flop from 0 to 1 requires 0 at T input, 1 at T input, 0 1 sequence at T input, none. Yes, so the correct option is option B. So we have a T flip-flop. So let me just write down the T Q n plus 1 0 0 0 1 1 0 1 1, this is 0, this is 1, this is 1, this is 0. So from transition from 0 to 1 requires 1 at the input. Now this is the last question of today's live session. I would like you guys to do first. It will take 5 to 6 minutes. Then I will show the solution. It says that the truth table of XY flip-flop is shown below. So you are given the truth table below. Design the flip-flop using JK flip-flop. So you have to design the below flip-flop using a JK flip-flop. So here are your four options and you need to select one of the option. I'll read the question again. The truth table of the flip-flop is shown below. Design the flip-flop using a JK flip-flop. So it will take 6 to 7 minutes. I'll just wait for you guys to. Size is very small. Okay. Let me just try to increase it. Is it visible now? Okay. So kindly do the question and write down the answer. Has anyone done it? It will take some time. I think a couple of minutes more. Yes. Are you guys doing it? So then I'll wait. So let me just show you the solution. If you are doing it, please carry on. Let's see a couple of minutes more, then I can show you the solution. So I told you whenever we have these conversion problem at hand, we need to do two things. First, find the required flip-flop and available. So the available is JK, the required is XY. We don't know what it is, so it's XY. Then what was the next step? We have to draw the characteristic table of the required flip-flop, right? So we have to draw the characteristic table of the required flip-flop. So how will you do it? We have input X, we have input Y, then we have Qn, then we have Qn plus 1. So how many cases will be there? 8. 0, 0, 0, 0, 1, 1, 1. There will be one more. Then Y is 0, 1, 0, 1, 0, 1, 0, 1. Qn. So I made a miss. Qn is then 0, 1, 0, 1, 0, 1. So how will we write the characteristic table of this? By taking help from the truth table that is given below. So Qn, x is equal to 0, y equal to 0, Qn plus 1 as per the truth table is Qn bar. So it's 0, so it will be 1, it's 1, it will be 0, right? Now next condition is 0, 1, so it is 1, 1. Next condition is 1, 0, so it is 0, 0. And again at 1, 1, we have a toggling, so it will be 1, 0, right? Now this was the second step of the 5 points that I told you to remember. Now the third point is you have to write the excitation table of the required flip-flop, available flip-flop, that is J and K, right? So before you write the excitation table of the required flip-flop, let me just write down the excitation table of JK flip-flop in general. What is the excitation table of JK flip-flop? So in general, this is 0x 1 x x1 x0. So you guys know this. Now Qn is equal to 0, Qn plus 1 is equal to 1. So 0, 1, it will be 1 x. Then we have 1, 0, it will be x1. Then we have 0, 1, so it will be 1 x. Then we have 1, 1, so it will be x0. Then we have 0, 0 will be 0x. Then we have 1, 0 will be x1. Then we have 0, 1, it will be 1x. And finally we have 1, 0, it will be 1, 0, it will be x1. Let me just cross check it. 1 x1 x0 x1 x x1 x x0 x1 x1, right. Now using this I'll make a boolean table with this k map. First for j, because we have to now supposed to write the boolean expression for the available flip flop. So first I'll write for j, so it's 1, then x, then 1, then x, then I have 0, 0 x, 0 x, x1. So this will be, here it is x, here it is y and q. So we have this thing and this thing. So my j will be equal to x bar. So it is 1 0 1 1, x bar plus y. My j will be equal to x bar plus y. Similarly for k, I have x, then I have 1, then I have 0, then I have x, then I have x, then I have 1, then I have 1, then I have x. So it will be like this and like this. So my k will be equal to, my k will be equal to x plus y bar. So j is equal to x bar plus y, j is equal to x bar plus y, k is equal to x plus y bar. That is option D. So this is how you do it, and I am pleased to see that most of you have done it correctly. So that was all for today's live session. If there are any doubts, do ask me. Yeah, any doubts, please type in. Yeah, yeah, yes. Yeah, you can do it, but this kind of simplifies the things. Yeah, yeah. Yeah, basically you are just continuing with the truth table, right? So the that was Lunia. So, but I hope I think you joined late. So I told the students you remember 5 points. So the point two of that, let me just show you this, because I gave them a methodology to solve it. So I didn't want to confuse them. So right, I think right, it should be right here, yeah. So the point two is make characteristic table of the required flip flop. So this was a truth table, so you can do it, there is no issue doing it like you have done it. But to make things simpler and to follow one methodology, I made this characteristic table. That's how I do it, and that's how I showed them to them. So that's why I made a characteristic table. I hope you got my point. So any other doubts from any other question? If not, we can close today's live session, and just an announcement. We usually meet at Sundays from 3 to 5 p.m., but I won't be available next Sunday. The next Sunday's session will be postponed. You guys will receive the notification accordingly. So thank you so much for joining. I think it will be postponed by 1 or 2 days. You will receive the notification of the session. Thank you so much. Thank you so much for joining.